Good afternoon, everybody. My name is Simone Melchionna. I wish to thank at first NVIDIA for giving me the opportunity to present our project and our results. And so I'm coordinating this project on Petaflop Biofluidics, and I'd like to tell you more about this. So biofluidics entails dealing with computational medicine and biological fluids as such. So biofluidics is an emerging field whose goal is to deal with carriers of nutrients, wastes, and other molecules in a physiological system. And biofluids include blood, which is the reference biofluid. So when we need to deal with biological fluids, we handle complexity, which is intrinsic to physiological systems. And complexity means the morphological details, differences in the physiological system, and also the complication arising at computational level to deal with such systems. So we cannot tame such complexity by brute force unless we adopt some interdisciplinary modeling. And so my main message here is that the synergistic effort between modeling, mathematical reasoning, and computational science has the potential to turn the computational model into an efficient technique and algorithms that can be used on leading-edge platforms. So this would enable us to have transformative advances. So let's start by looking at the blood system, at the circulatory system, which is made of course, of several vessels, and dealing with hemodynamics has an enormous societal impact. But besides understanding the behavior of such a non-trivial fluid as blood, I would talk about it for hours, of course, cardiovascular hemodynamics has this impact because we have to do with a very complicated maze of vessels that carry nutrients from the heart to the periphery. And blood flow is heavily influenced by the individual components of blood and by the geometry of the vessels. Okay, so this is a very complicated motion, and heart disease happens as a result of these actors. So atherosclerosis is one of them. So here you're seeing plaques forming into coronary arteries, for example. So plaque rupture is what happens from time to time. This is a rare but dramatic event, and which is followed by flow interruption, and so heart attack and stroke may happen. So this is the first cause of mortality in Western society, and so the goal here is to forecast when and where and how sometimes plaque form. So GPU computing is particularly appealing for daily clinical practice, potentially, because for two basic reasons. First is that the high performance to price ratio, and secondly, the time criticality. Of course, you need to intervene in a point of rescue very soon, as soon as the disease happens. But at the same time, it's very important to have predictive power. So computational medicine here means the possibility of predicting the occurrence of disease, very timely, of course, and with high accuracy, and of course, non-invasively. So computers are non-invasive in this respect. So let me give you a few more details about the systemic aspects of the coronary network. So any point of the vasculature depends on flow conditions in faraway regions of the system. So if something happens in one place, it would reflect throughout. So this is an all-to-all connectivity of the cardiovascular system. And so the only possibility to determine regions of high risk of plaque formation, of plaque rupture, is through computing the real complete arterial geometry. So let's look at this clip showing the results of a real simulation. So if we zoom in closer and closer into the coronary tree, realized that blood is not made of just one component, it's not a continuum, but it's made of two majority components, plasma and red blood cells. So as shown here, red blood cells move, tumble, and whirl in erratic ways across the system. And so if we look closely also at the motion of plasma, at the streamlines of plasma, these are non-regular. These are intermittent and have somehow wild behavior. So the consequence of this behavior is that we need to simulate concurrently the dynamics of red blood cells and plasma. So we cannot work out some sort of effective medium here. So solving the complex fluid motion requires to cope with wide ranges of scales, ranging from microns, 10 microns, which is the scale of cells, red blood cells, to centimeters, which is the size of the heart, and complex geometries. So we have also several computational actors, and time critical, of course. So we need to deal in particular with arbitrary geometries via some non-conventional computational method. For example, we cannot use Navier-Stokes solvers. This is highly impractical and computationally demanding. And so we have devised what we call concurrent multiscale method, which is a way to challenge such computational complexity. So the fabric of the computational methodology is shown here. The multiscale method is based on a unique combination of the Lattice Boltzmann and molecular dynamics techniques. Lattice Boltzmann handles the fluid plasma, while molecular dynamics handles the suspended bodies, the red blood cells. And so this dual technique relies on a uniform Cartesian mesh that allows to handle both on-mesh quantities and off-mesh quantities. And the multiscale approach is not simply gluing these two methods together, but we need to design and model the exchange of information between these two components, Lattice Boltzmann and molecular dynamics. So the multiscale method is in itself very general, since it allows to describe complex fluid in many different conditions and under generic confinement. So to turn these ideas into reality, we have written the software MUFI, standing for Multiphysics Simulator. MUFI enables to simulate different fluids as much as different suspended bodies and molecules, ranging from microscopic to macroscopic scenarios. So MUFI is a multi-platform. It can be used on clusters of CPUs and GPUs and massively parallel architectures. So the code has a high degree of abstraction, in particular from the geometrical complexity and parity, by using indirect addressing methods. And so we can then simulate very different systems, physical, chemical, and biological systems, up to physiological systems. The example depicted here is that of DNA translocation in DNA sequencing experiments as done by us with the MUFI software. So the architecture of MUFI is shown here. So the architecture, the design reflects the several components accommodated in the computational environment. So the fluid and particles execute concurrently and exchange informations in a very tightly bound way at every time step. There are non-blocking communications that allow to partially overlap communication and computation. And the structure of the multiscale methodology presents several critical sections which are equally distributed over this time stretch, most notably regarding the mechanical and hydrodynamic forces exchanged between particles and surrounding plasma. So we have a number of algorithmic challenges, in particular when dealing with biological networks. For example, partitioning the highly irregular geometries into domains which are assigned to the LB and MD solvers. And this partitioning should guarantee good load balancing on any number of partitions. Second, we need to perform parallel molecular dynamics on irregular domains, and a situation which recurs frequently in, for example, simulating porous media or other confining situations. And third, we need to design an efficient, scalable, and portable communication system. So we have faced these three intertwined issues separately. So let's look at a typical domain partitioning of a coronary tree. So this is shown here for a limited number of partitions, but as we increase the partitioning, as hundreds of thousands of domains, the regularity of domains is completely lost, and interconnectivity goes out of control. So we need a good partitioning scheme such to assign the same domain to the fluid and particles solvers. And this choice would preserve, of course, data locality, avoiding circulation of large data sets over the network. And a solution is offered by those tools based on graph partitioning, graph-based tools such as Medis and Scotch. These are popular softwares in the community. However, the solution given by these softwares is suboptimal because one achieves an equal distribution of mesh points over domains. However, these tools bear no notion of the global geometry of the system. So as the number of domains goes high, domains become over-connected and scalability rapidly deteriorates. So our strategy to improve scalability is to reformulate the domain partitioning as a guided procedure. So basically the first step is graph-based, and so this works well up to 256 domains, and this is done by using, of course, Medis or Scotch. And basically what you see here on the top left graph is that the distribution of domain neighbors stays constant up to this point, stays compact, which means below 10 almost. The second step is flood-based, so it's a flooding algorithm in order to further repartitioning these 256 domains by preserving the boundaries of the superdomains. And so as the partitioning marches on, the number of neighbors remains compact and small, and basically below 20 up to 4,000 total domains. So this guided procedure achieves both good load balancing and a limited number of domain neighbors. The second challenge regards particle dynamics in irregular domains. So as you see here, you need to follow the motion of particles as they move in completely irregular domains, including migrations across the very regular surfaces between different domains. And in addition, we need also to compute the forces exerted between red blood cells from intra and inter-domain contributions. So clearly these issues can be handled easily in conventional molecular dynamics when you deal with simple slabs, parallelipipeds, and all that. But here we had to design from scratch a new technique. So we have elaborated a way to follow the movement and migration of particles. So the method is based on Lagrangian tracking, which means that the underlying mesh is used to track the mesh points that are closest to the red blood cells at every time step. And a membership test is used to determine if particles leave or enter a new domain. So this digitalized location in the domain is obtained with an order n algorithm, which is basically used on a binary search algorithm. Second challenge is to compute forces, and these are computed by further tiling the irregular domain. The tiles are colored according to the overlap with the domain frontier. So as shown here, internal frontier and external tiles are assigned to some color, and some tiles have a special color if they cover multiple intersections. So the membership test assigns particle to containers and selectively transfer information and particle position and velocities to domain neighbors by occupying the bandwidth at the bare minimum. So by using a data structure that takes advantage of this hierarchical level, we have again an order n effort, and which is particularly efficient on GPU computing. So our application runs on GPU clusters such as the TSUBAME 2.0 supercomputer, and you already know the figures about this computer, so I'm not going to repeat them. We have about 2 million cores to deal with by the definition given this morning. So the communication pattern on this multiple GPU system needs to be designed with care. To fix ideas, we consider this diagram that shows the computation of quantities in the bulk and at the boundary of a computational domain from the GPU side. So once the calculation is completed, data are passed from the GPU to the CPU, and the CPU exchanges data, boundary data, with the other CPUs. So the standard way of serializing computation and communication is quite inefficient on multiple GPUs. The reason being that during CPU's arbitration, GPUs sit completely idle. However, CUDA supports independent streams of execution that allow to overlap partially communication of boundaries with computation of bulk quantities. So this picture shows now the modified diagram illustrating the stream-based paradigm as implemented in MUFI. So let us now move back to the clinical application. The computational task is completely driven by the clinical requirements. So we have a huge mesh to resolve the atherosclerotic risk map to sufficient accuracy. This means a mesh resolution of about 10 microns, which is the size of red blood cells, and extending over 10 centimeters, which is the entire myocardial region. So for a complete arterial tree covering the entire heartbeat, this entails 1 billion voxels and 20 billion lattice degrees of freedom to deal with. And being in time resolution 1 microsecond, the complete heartbeat is covered in about 1 million steps, of course. And physiological conditions impose to have something like 450 million red blood cells, half a billion red blood cells. So the full bounding box is made of 100 billion mesh nodes. Of course, we don't handle all of them, but we employ indirect addressing to account only for the active nodes, since in coronary arteries, just 1% of them are active, which means the 1 billion figure I gave above. So on the TSUBAME 2, we now can run our system and compute floating point operations. So in order to compute flop counts, GPUs don't have hardware counters, so we count floating point operations by using tools available on the CPU side, by considering the equivalent codes that work on the CPU, and timings are instead given by the high resolution counters available from the CUDA profiler. So overall, we obtain sustained performance above 600 teraflops, almost equally shared between the MD and the coupling components. The LB, the Lattice Boltzmann part, is strongly memory bound and does not exceed 400 teraflops. So given the widespread of critical computing sections of the methodology, these figures are highly gratifying. And we can now move to the strong scaling behavior. Our system is still the 1 billion, half a billion red blood cell system. And so the elapsed time shows excellent scalability of all components, up to 4,000 GPUs. So in the breakdown of each kernel, the relative time stays pretty constant for the 3 components. So this means that there is no degradation of one part over large partitions. So let's look at the Lattice Boltzmann algorithm alone. We can now compare the performances of the algorithm and compare it directly with the timing obtained on the Blue Gene P architecture. This component of the multiscale methodology scales basically linearly over 4,000 GPUs, as much as over 300,000 Blue Gene P cores. And the efficiency stays always above 80% on both platforms. So by comparing the timings obtained on the TSUBAME 2 platform with the one obtained on the JuGene, which is the Blue Gene Pin platform in Germany, we obtain a net improvement of a factor 7. So this figure should be compared with the 2.2 ratio in peak performances of the 2 installations. And the parallel efficiency of the multiscale methodology is shown here, and it's measured over different numbers of GPUs, of course. The data shows efficiency close to 100% up to 1,000 GPUs, and a slight deterioration to 80% for the full configuration of 4,000 GPUs. And let me also recall that domain partitioning is highly nonlinear as an algorithm, and the communication pattern can have an irregular trend as we increase the number of domains. So the consequences of such irregularity is that the bandwidth is differently occupied and even presents cases of super efficiency above 100% as compared to the 256 domains. So the measured bandwidth for 4,000 GPUs is about 600 megabytes per sec, which is highly satisfactory on the InfiniBand fabric of TSUBAME 2. So let me conclude by presenting a clinical application, a real-life clinical application, and the application addresses a crucial issue, that is the robustness of the coronary arterial network of some patients against the development of atherosclerosis from a systemic viewpoint. So one particular quantity that measures the degree of robustness to plaque growth is the pressure drop occurring over the network due to the global rearrangement of the flow. This pressure drop measures basically how much the myocardium will be oxygenated. Therefore, if we have a strong pressure drop, that will be a bad sign. So we have analyzed several different scenarios, each associated to single or multiple occurrences of plaques in regions where plaques have a high risk to form. We have done some previous calculation in that respect, and which happens basically past the arterial bifurcations. And different case studies are analyzed for different levels of plaque severity, and this gives us very precise indications if we need to have a surgical or percutaneous intervention on the patient. So this is what I meant in the first slide with the computational medicine and being predictive about the occurrences of the disease. So let me conclude by recalling the three elements that enable new advances in computational science: modeling, algorithmics, and high-performance computing. So biofluids pose new challenges, and we have responded with this multiscale methodology, which handles particles and fluid in generic physiological conditions. We can now do massive parallelism of irregular morphologies, which is optimally suited for GPU computing. And finally, we have realized that multi-platform software that runs on multi-platforms, which means either CPU-based or GPU-based. And so for the first time, multiscale computing has enabled to perform personalized medicine, ranging from red blood cells to entire heart size. And today, the multiscale cardiovascular simulation is being used in leading hospitals as an emerging procedure in clinical activity. Thank you very much for your attention.